Jan Stafleu from TNO, the Dutch Geological Survey. Hello, Jan, and you will talk about the surface modeling as it is done at TNO. So just a few words about Jan. Jan combines geology and geomodeling with also a background in programming and software design, and he's project manager dedicated to the shallow subsurface at TNO. And especially, Jan is involved in the national initiative for high-resolution 3D geological modeling, where these geological models serve various applications, such as water resources or subsurface use planning. So Jan, please, the floor is yours now, and I think for about 1 hour presentation.
Yes, thank you very much, Philippe, for the introduction. We'll share my screen for presentation. There we go. So if everything went well, you now see a beautiful model of the Dutch subsurface. Is that right?
Yeah, it's okay.
Okay, thank you. So I'm going to talk about subsurface modeling at the Geological Survey of the Netherlands. And I will start with this aerial photograph of part of the Dutch lowlands. And as you can see, it is flat, it is wet, it is protected by dikes, it is windy, and there's not an awful lot of geology that you can see or observe in the field. So that is also basically the reason why we put so much effort in building detailed geological models, because it's basically the only way in which we can visualize geology in our country. So what I'm going to talk about is the models that we make on a national scale. So they cover the entire country, and some of the models also cover the Dutch part of the North Sea. I'll spend quite some time explaining how these models are being made, so the workflow, so to speak. Then I will look into the applications, how are these models used and how do they serve our users. Talk a little bit about the key registry of the subsurface. That is a law in the Netherlands that obliges, that makes sure subsurface data is collected and used. And I will end, of course, with some concluding remarks. So the national models, there are 4 of them, and they serve 3 different depth ranges and application domains. And they're also different in the type of data that they use. And from bottom to top, we start with the DGM-deep model, which goes to several kilometers in depth and originally was used by the hydrocarbon industry. And now more and more it's being used for geothermal energy. And the data type, obviously, for this kind of models is seismic data, accompanied with some 3,500 wells. If you go closer to the surface, then we come in the realm of groundwater and drinking water. 60% of the Dutch drinking water comes from the subsurface. So we need good models to support the management of that drinking water supply. Those models are called DGM and REGIS. DGM, a geological model, REGIS, a hydrogeological model. And they have a range from land surface up to more or less 500 meters and sometimes a little bit deeper. And then on top of that, there's the GeoTOP model, which has a very strict depth base at 50 meters below sea level. It's a very detailed model. It has a layer structure that is very detailed, and within those layers, voxels are being filled with lithology. So apart from stratigraphical layers in GeoTOP, we also have lithology, and we will see that there are additional parameters as well. GeoTOP is used in the built environment, and we'll see more applications later on in the presentation. Both GeoTOP and DGM and REGIS are based on boreholes. In GeoTOP, we use hundreds of thousands of boreholes, and in DGM and REGIS, we use about 25,000 boreholes. So the DGM-deep model, and this is basically the one and only slide I'm going to show about the deep subsurface. The remainder of the talk will be about the other three models, DGM, REGIS, and GeoTOP. The DGM-deep model covers both the onshore and offshore part, because a lot of the hydrocarbons that we mine in the Netherlands come from the North Sea. They cover stratigraphical strata from the Carboniferous to the Neogene. Seismic data is the main data source, accompanied by some 3,500 wells. And basically, the model is a stack of raster layers, horizons interpreted in seismic data, with a resolution of 250 meters, so a cell grid size 250 meters. The geological units have a top, a base, a thickness, and associated uncertainties. DGM and REGIS is also a layer-based model, so in that way it looks like the DGM-deep model. Their resolution is a bit higher, it's 100 meters rather than 250 meters. It's only available onshore, and a big difference is that it is entirely based on boreholes, borehole descriptions, which are interpreted in terms of stratigraphical units for the DGM model and then hydrogeological units for the REGIS model. And all these boreholes are in a single national borehole description database. That is one of the big assets that we in the Netherlands have in the Geological Survey, that all the data that we need is available in a single database, which also has a standardized coding system. So all boreholes are described in the same standardized way. We have also to say that we have very good quality, high quality borehole descriptions in the database, but there are also many boreholes that are quite old or have lower quality because of any kind of reasons you can think of. So we have to work with the data that there is, partly gathered by ourselves, by the survey itself, and partly delivered to us by third parties. And all the data is publicly available. You can go to the website, TNO. There's an English version, and you can look at the location of these boreholes and click on them and see the borehole description. So these are two pictures of these two layer-based models, DGM and REGIS. DGM is the geological one of the two with stratigraphical units, a resolution of 100 meters, and a stack of raster layers with top, base, and thickness of each stratigraphical unit, and the uncertainties associated with these tops, bases, and thicknesses. And then on the right-hand side, you see REGIS with hydrogeological units. And of course, you see that the models are they look very similar. And that is because we model hydrogeological units, so the aquifers and aquitars, within the context of the stratigraphical units of DGM. So for instance, if you look closely at the model at the bottom right, you see this blue layer, and which is also present in the DGM model on the left. And within the blue layer, you see two dark blue layers. Those are aquitars, or clay-rich layers, modeled within the blue aquifer, which is sandy in nature. So the dark units that you see in the bottom right are the water-resistant aquitars, and the light colors is basically the matrix of sand, which also serves as an aquifer, as a container for drinking water. REGIS is the first of the three models that also has parameters. So it's not only the geometry, the top, the base, and the thickness of a stratigraphical unit, but it is also the hydraulic conductivity. And hydraulic conductivity then may vary, the value of the hydraulic conductivity may vary within the aquifers and aquitars. I will see some examples of that later on in the presentation. Then the third shallow subsurface model is GeoTOP. It is both a layer-based model, which looks very much, is very similar to the DGM model, but it is based on 600,000 borehole descriptions. So basically all borehole descriptions that are available in our database are being used. A large amount of these borehole descriptions are manually made, like you can see on the photograph. So they are quite shallow. Maybe they are 5 meters in depth, or maybe 10 or 12. So they give a lot of information about a very shallow subsurface. That is also the reason that GeoTOP is not very deep. It's 50 meters below sea level at maximum, whereas DGM and REGIS reach depths up to 500 meters. If we look a little bit closer on the map, in the area around Utrecht, and Utrecht is also the location where I am right now. That's where the main office of TNO, of the Geological Survey, is situated. And on this map, you can see the scale bar on the left of 10 kilometers. All the orange dots here are boreholes that we can use in the GeoTOP model. So there's a lot to be used. And this is what the GeoTOP model in this area looks like. So you see the different colors, which come from a layer-based model. Layer-based model is then voxelized into a rectangular grid of voxels, each measuring 100 by 100 meters in the horizontal direction, so the same resolution as DGM and REGIS, and 50 centimeters in the vertical direction. And each voxel then contains several parameters. The first one is the stratigraphical unit the voxel belongs to. That is derived from the detailed layer-based model. And then within each stratigraphical unit, we estimate the lithological class the stratigraphical unit contains. So that is what the next slide shows. You can see there are 7 different lithological classes: clay, sand, and peat. That is basically the soft soil, which occurs a lot close to land surface. And then sand, fine-grained sand, medium-grained sand, and coarse-grained sand in the remainder of the volume. And the 7th lithological class is composed of the anthropogenic sediments. So that can be sand used to raise, to elevate land surface. That's basically the largest part of the volume, but it can also be waste, for instance. So landfills are also modeled as part of geology and have then a lithological class as anthropogenic sediments. We not only model this directly in one model run to produce a picture like this, we do that a number of times, 100 times to be exact. And from these 100 model runs, which look very similar but are also a bit different from each other, we can calculate the most likely outcome. That is the picture that you are seeing right now. But we can also calculate probabilities. So we not only estimate that a voxel contains coarse-grained sand, but we also say from the 100 model runs, it produced 80 times coarse-grained sand and maybe 20 times medium-grained sand. So the probability for coarse-grained sand is 80%. And that also gives you already a kind of an estimate for the model uncertainty. If you know that there is one lithological class which has a very high probability of occurrence, then you have a lower model uncertainty than when you have a voxel that has a large number of different lithological classes modeled at different probabilities. GeoTOP is still work in progress. You see that there's a large part missing in the east, and there's also a smaller part missing in the southern part of the country. So that is what we are working on right now in the coming years, and we hope to finish to complete the model by 2027. So the general modeling workflow to build all three models is depicted here. We start with a conceptual model. That is basically the idea the geologists have when they look at a certain region in the Netherlands. What are the stratigraphical units we are going to model? And what are the stratigraphical relationships between those different units? From that conceptual model, we start with a process of mapping and interpretation. Mapping is to delineate the area of extent or the spatial extent of each stratigraphical unit so that we know where in a spatial context we can expect different units to occur. At least we delineate an area where we know the unit will be present, and everything outside we know for sure that the unit will not be present. Then we look at the boreholes, and these boreholes will be interpreted. They can be interpreted by hand, like in DGM and REGIS, or they can be interpreted using automated procedures. That is the way that we use for GeoTOP. Then we do the actual modeling using the data from the boreholes and the spatial extents from the mapping effort. We build the layer-based model, and if it is GeoTOP, we will also fill the voxels with lithological classes and other attributes. And then that is the Mr. Clouseau on the right-hand side of the picture. That is the quality control. When colleagues who haven't been working in the modeling and mapping will check the model, look for strange things they don't like. And if they agree that the model is okay, then we are ready to deliver it to the public. And usually a modeling program project for a region of the Netherlands, starting with a conceptual model, do the mapping and interpretation, the modeling and the quality control, usually takes about 3 years. Well, before I dive into some details and look at each of the different parts of the workflow in more detail, a few words about the integration of the layer-based model, because so far we've talked about DGM, REGIS, and GeoTOP as separate models, and we already saw that DGM and REGIS are very closely related to each other. The hydrogeological layers in REGIS are modeled within the context of the stratigraphical units in DGM. But GeoTOP used to have its own layer-based model for the shallowmost part of the subsurface, which is of course also modeled, but in less detail, in DGM and REGIS. So that is quite inefficient, and it also led to inconsistencies between the two models, between the three models. So we decided to fix that by building a single national layer-based model, which is detailed in the upper tens of meters, so it can serve as a framework for the voxel model of GeoTOP, and has less detail in the deeper parts, so it can serve as a framework for the hydrogeological model of REGIS. And this workflow for the integrated layer-based model leads to a consistent layer-based model of the shallow subsurface of the Netherlands, and it's much more efficient than having separate workflow in operation at the same time. So, in this integrated layer-based model, for the deeper part of the subsurface, we still use the manually interpreted boreholes in the same way as we used to do in DGM and REGIS. So it's geologists looking at borehole descriptions and deciding where stratigraphical unit starts and where it ends. And for the shallow part of the subsurface, where we have all these manually made auger holes, we use automated procedures to give a stratigraphical interpretation to the boreholes. So let's have a look at mapping and interpretation. How does this go about, interpreting boreholes? Basically, most of the work is being served by or being done in ArcGIS Pro. So we construct maps of stratigraphical of the spatial extent of stratigraphical units in ArcGIS Pro, and we store our polygon data in an enterprise geodatabase. Part of the boreholes are then being interpreted manually using cross-sections and maps that already exist. And within the borehole descriptions then is decided by the geologist the top and the base of a stratigraphical unit, coupled at the borehole description intervals in the borehole description. And part of the procedure is being automated, like I said, for the shallow boreholes. The result of the borehole interpretation is then stored in the DNO database for future reference and also for the general public to have a look at it, or if they want to use it in their own modeling efforts. But it's of course also transferred to the next step in the modeling procedure, which is the layer-based modeling. So about automated borehole interpretation. This is a simple workflow showing how that works, and it works in a very iterative way. It is a geologist or geomodeler who is writing the code, so it's not an IT personnel who writes programs, but is basically the geologist trained in using Python to do that. Using borehole data from the database, using existing geological maps that have of course been digitized, so we can put it in ArcGIS Pro and make use of it to define the spatial extent for geological unit. Over the spatial extent in the of the geological unit, we plot the available boreholes. Yes.
Participants.
I'm sorry.
Sir,
Sorry, Jan, please continue.
Oh, okay. I thought there was a question, which is okay, by the way. If somebody wants to ask a question, it's fine with me. So in the ArcGIS Pro environment, the geologist plots the borehole data that is available together with the spatial extent he or she has so far being drawn. Then it goes into Python, and in Python, the boreholes that fall within the spatial extent, so it will not look at the boreholes that are outside the spatial extent, the boreholes in the spatial extent, and then being analyzed and different criteria, sedimentological composition, for instance, or the stratigraphical position with respect to other stratigraphical units, is then used to decide, is the stratigraphical unit present or absent in this borehole? And if it's present, what then is the top and the base of that stratigraphical unit? That he plots on the map and decide, am I satisfied with this outcome? Maybe I see a lot of red dots where I expect a lot of green dots. Then I'm not satisfied, and then I have either to adjust the criteria in the Python script, or maybe I have to adjust the spatial extent. Maybe the spatial extent has to be larger or it has to be smaller. So it is a very iterative way to produce tops and bases of one particular stratigraphical unit. The great advantage is, after that you have done this, you can put as many boreholes as you like into the system, and it will produce within minutes stratigraphical interpretations for that particular stratigraphical unit. And it will do that always in the same way. It's not so that it will give you a different interpretation on Monday than on Friday, but it's sometimes the case if you ask a geologist to do the job by hand. So I'll just give an example of how this works. This is a conceptual model of the Holocene sequence, the Holocene coastal sequence in the southwestern part of the country. You see a wedge of Holocene deposits dipping from the east to the west. You see the dipping plane in purple of the Pleistocene sediments, on top of which the Holocene deposits are deposited, of course. There's a coastal barrier, beach and shore face deposits. On top of that are Aeolian dunes. And back to the east of the coastal sequence. There are tidal deposits in green, there is peat in red, and fluvial deposits from the River Rhine in light blue. And there is a thin peat layer just underneath the fluvial deposits of the Rhine, the light blue deposits, which is called the basal peat, right above the Pleistocene deposits. We're going to look for, as an example, to first at the Aeolian dunes. Oh, sorry. This way. By looking not at the conceptual model, but at the boreholes. So here are the borehole descriptions in the area. We have sand in yellow, clay in gray, and peat in brown. And for the coastal sequence, for the coastal dunes, we look at the map. That is the spatial extent that was made. And the boreholes within that spatial extent are the boreholes right here. And then in the borehole description, from top to bottom, we analyze the description intervals and we look for something else than sand, because the dunes are obviously made of sand. So we're looking for something other than sand. If we found that, then we say the bottom of the stratigraphical unit is at the top of the sediment that is different from sand, and the top of the stratigraphical unit is at land surface. Then the next example is then the basal peat layer, this thin peat layer that is on top of the Pleistocene sands, which you can see dipping from the east to the west. And from previous maps, we're using now an older map that we already have, which shows the depth of the Pleistocene, the top of the Pleistocene deposits. We know that we can expect this basal peat layer to occur in a bandwidth, in a buffer zone, above or below this pre-established, earlier mapped Pleistocene, top of the Pleistocene deposits. So somewhere between those dotted lines, we know that we want to look for this basal peat layer. And at this time, we're going to look at the borehole descriptions from the bottom to the top, so that the first description intervals that we see are sand, Pleistocene sand. Then if we encounter a peat layer, the first peat layer that we encounter, we know that it is the basal peat layer. And it is important that we find this first peat layer within this buffer around the surface of the top of the Pleistocene that we know from this pre-existing map. Because if we, for instance, in the borehole that is to the right of the third circle, you can see that sand of the Pleistocene is followed by sand, fluvial sands from the Holocene. And then very close to land surface, there is a peat layer, but that is a different peat layer. So if we would only set a criteria to look for the first peat layer from the bottom of the borehole description, then we would find the wrong peat layer. So it's sedimentological, lithological descriptions that we use as a criterion. It's the spatial extent, where units occur or not occur, and it is also other data, geological information that we use to correctly stratigraphically interpret the boreholes. So what is then the information that we're going to use in the layer-based model? Well, suppose we have these two boreholes here, and part of these two boreholes are interpreted as an orange unit. And in both boreholes, we have the top of that unit, and in the left borehole, we see a true base, which means that another older stratigraphical unit is also present. So we know exactly what the bottom of the stratigraphical unit is. And the borehole on the right-hand side, we know a minimal base, but in this case, the bottom of the stratigraphical unit coincides with the end depth of the borehole. So we're not sure if that is the true base, or maybe the unit will still continue for several meters. But still, that information can be used in the layer-based model, because whatever the layer-based model will estimate, it will have to be at least at this minimal base, the location of this borehole. And then there's a third kind of base that we can find in the boreholes, that is the absent base. In this example, it is the red unit, and on the right-hand side, we have a top and a true base, and on the borehole on the left-hand side, this unit is absent. But it's not, we not only know that the unit is absent, we also know that an older stratigraphical unit, the light pink color and the orange one underneath that, is present. So the unit itself is absent, but the stratigraphically lower unit is present. And we want to use that information as well, because otherwise things can go wrong, as is illustrated in this picture. So for this same red unit, on the left and the right, we have a true base, and in the middle, we have an absent base. And if you would interpolate the boreholes on the left and the right without taking into account the absent base, then we would have this horizontally dotted interpolation, horizontally dotted surface, which crosscuts the orange unit. That's not what we want. So we want to steer the interpolation along the absent base. And the modeling then, of course, also have to make sure that the red unit will remain absent in the model at the location of this middle borehole. So the next phase is modeling layers and voxels. And modeling layers as an input has, of course, the true, the minimal, and the absent base that we have in the boreholes. We also use auxiliary data points. Those are data points in areas where we have a lack of real data, or maybe very complicated areas in which we need some additional data to model the complicated geology that we know exists over there. We use, of course, the spatial extent, so the areas where we know the stratigraphical unit exists, and there are the faults. The data goes into an automated workflow with interpolations in ISATIS, and ISATIS is a geostatistical software package developed by GeoVariance in France, and which is capable of handling many borehole data. And that is a big difference, a big advantage, I think, of this software over, for instance, Petrel. Petrel is very good in handling large amounts of seismic data, but not a large amount of well data. And ISATIS is basically the other way around. It's capable of handling enormous amounts of point data. And for each stratigraphical unit, what we do is we first create a trend surface of the base of each unit. And a trend surface is basically a rough, coarse interpolation of the base. It's basically, if you step back, what is the general trend of the base of the stratigraphical unit? Where does it go up? Where does it go down? Then we compare that surface with the borehole data and calculate the residuals, so the difference between the depth of the unit observed in the borehole and the trend surface. And then these residuals are being interpolated using kriging with the geostatistical parameters like a BRGM and search neighborhood. If you then calculate, you interpolate a residual surface, which is then combined with the trend surface to arrive at the final base of the stratigraphical unit. So we model bases, and by stacking these bases on top of each other, we can build a consistent layer-based model and also derive the tops and the thicknesses. So tops and thicknesses are not interpolated, but derived from the overlying our tops are derived from the overlying bases, and thicknesses are calculated as top minus the base. So we then have an integrated layer-based model of DGM and GeoTOP. You can see in the flying carpet mode the deeper parts of the model, the green, the blue and the orange unit. And then on top you see in much more detail the layers of the GeoTOP model already voxelized to these rectangular voxels. So that's voxels is also the next step in the modeling procedure. So the input data for the voxel modeling is the layer-based model, voxelized, as we saw in the previous picture. And then also the borehole descriptions, the same one as that have been used in the construction of the layer-based model. But then the borehole descriptions are converted to lithological classes, to these 6 geological classes that we use in GeoTOP. This goes into ICTs again, an automated workflow again with simulations. And the simulations use a variogram, a neighborhood, with geostatistical parameters, and an additional parameter compared to the layer-based model, which are the proportions. We'll come back to that later. And the automated workflow then results in 100 equiprobable model runs, so 100 different predictions of the distribution of lithological class within each stratigraphical unit. From those 100 runs, we can calculate the probability of occurrence for each lithological class, and from the probabilities then an estimate of the most likely outcome is being calculated. Because many of our users don't like to work with 100 different models, they just want one model that is the best estimate of the lithological composition of the subsurface. So something about proportions. We model each unit separately because they have different geostatistical parameters, different variograms, different search neighborhoods, but also different proportions. And for instance, the upper 2 graphs here show flood basin deposits and channel belt deposits of the River Meuse. And you can see, of course, that flood basin deposits are characterized by clay, and the channel belt deposits are characterized by sand and gravel. And you can also see that some units, like the one in the lower left, are very homogeneous. That unit consists of almost only clay sand, or units can be very heterogeneous, like the stream valley deposits on the lower right, which have many different lithological classes mixed in one stratigraphical unit. So you need different geostatistical parameters to model each of these units in a proper way. You can also see this as a result in the probabilities of the voxel model. So on the left is the stratigraphical model being voxelized, the layer-based model voxelized in GeoTOP, and on the right you see the probability of occurrence of 3 of the sandy lithological classes. And you can see that each of the units have different characteristics and also different probabilities of occurrence of the lithological classes within those stratigraphical units. In this particular piece of GeoTOP, you can also observe a different phenomenon, and that is that some strata are, of course, dipping. Not everything is flat in the Netherlands. It's a flat country, but in the subsurface, we have dipping strata, and you want to model that properly in the voxels as well. And if you do that, you have to do that very carefully, because if you look at the data, for instance, here on the left, there are 2 boreholes with a clay layer in it, and they are, of course, correlated with each other. It's the same clay layer. And if you interpolate that as it is, if you put that in ICTs and ask, can you interpolate this data, then it will produce 2 different clay layers which are not connected to each other. But that's not what you want. So we have invented a solution for that, in which we unfold the data. So now they're folded, and we unfold the data to the original situation as they were when the sediment was being deposited. Once it's unfolded, we do the interpolation, which goes horizontally, but now the clay layer is at the same level, so we will have a connected clay layer, and then we fold back the result to the situation as it is today. You can see the voxels aren't really dipping, but there's kind of a staircase which shows that there's one clay layer rather than two. So the result is then a layer-based model for the deeper subsurface, and on top this 50 meters thick piece of geotop, which is now filled with lithology, sand, clay, and peat. Then the last step in the whole process is the quality control. So colleagues who haven't been working on the model itself, they will look at the model. They are experts on the region. They're also familiar with the way in which we construct our models. They often have worked on other models. And they will systematically check cross-sections, maps, 3D views, whatever they want, to look for defects, to look for artifacts. And basically, the main thing they are looking for, is this a geological plausible model? And what is the quality of this model? And is the quality sufficient to be published, to appear on our portal? Or is there still work to be done by the modeling team? And the examples, I think, are, if you do modeling yourself, you recognize these kind of artifacts and problems, which you want to solve, of course, before you publish the model. We soon find out that if we have a project that takes 3 years to accomplish, and we have QC at the end, and you then find a defect in the conceptual model or in the mapping, you have to go months or maybe years of work back in time and redo something, which takes, of course, a lot of time. So we soon find out, well, we need quality checks at all major model components. So we're checking conceptual model, we're checking the interpretation of the boreholes, we're checking the spatial extent of the units, we're checking the layer-based model, and we're checking the voxel model. But we still takes a long time, 3 years, and with intermediate quality control moments, it takes a long time to build a model. So we're also looking at how are ways to see earlier in the process what the result is of what you are doing. So if a geologist is working on Python scripts or interpreting boreholes by hand or drawing spatial extents of units, can he or she then quickly see what the result of his work is in the layer-based model. She doesn't want to wait for 3 months before the geomodeler produces a new layer-based model with her interpreted boreholes, but she wants to see the result immediately. We're now experimenting with a kind of fast-forward layer-based model based on GenPy or maybe on another modeling tool. We're not sure about that yet, which is much faster than the whole rather complicated procedure we designed in ECTs to make very nice, to make great models. But to have a kind of fast-forward, maybe you can call it quick and dirty, impression of what the model will look like if you change the interpretation of a set of boreholes. But that's something that we are looking in right now. Well, after QC is being done and everybody is happy, and management says, okay, I've seen the model, I've heard the advice of the QC team, which is positive, we can now publish it. Then it's time to deliver the model on our web portals. And we have different ways of dissemination. The best known are the web portals, BroLoket and DynaLoket, which are public, so you can go to it and have a look at it. You can see a map of the model, create cross sections on the fly. You can click on locations and see virtual boreholes. You can also have a look at the real boreholes that have been used in the model and the stratigraphical interpretation we've attached to the boreholes. And you can see maps of the tops and bases and thicknesses of the layer-based model. We also have a subsurface viewer, which is a piece of software that you can download from our portal. You can install it on your PC or laptop, and then you can also look at the model, at the models DGM, REGIS, GeoTOP in 3D. And relatively new, published last year, are 3D web services, which have REGIS II and GeoTOP in such a way that you can look at them in 3D in your browser. That is something that everybody can do. And if you have a GIS package like ArcGIS or QGIS, you can easily import the model in your GIS environment and combine the data of the model with your own data, for instance. And on the lower right, there is the more classical delivery of tops and bases in ArcGIS maps. So we deliver the data, the interpreted boreholes and the faults, and we deliver the tops and bases of the stratigraphical units, and also in a very simple data format, the voxel model. And a very nice development last year was a model delivery in the Polish way. So the Polish Geological Institute created Geo3D, which is a 3D geological viewer in the browser environment. So you do not need to install software to look at GeoTOP in this case in great detail with great functionality online in your browser. Then something about applications. And the REGIS model is, well, basically in the Netherlands, it is the standard model that is being used by everybody who is making groundwater flow models. So REGIS is a static model. Water doesn't flow in REGIS. We have to make a groundwater flow model, but then the geometry in the groundwater flow model is almost always based on REGIS II. And some people now use GeoTOP to create more detail in the upper part of the REGIS model. REGIS II has aquifers and aquitars, and these aquifers and aquitars are being parameterized with hydraulic conductivity. And hydraulic conductivity may vary in the horizontal direction throughout the hydrogeological layers, the aquifers and aquitars that are in the model. So you can see in the map on the left a horizontal hydraulic conductivity of one of the aquifers, and on the right you can see a vertical hydraulic conductivity of one of the aquitars that are present in the REGIS model. Then for GeoTOP, if you want to use that in the groundwater flow model, it is 3D, so we need hydraulic conductivities in each of the voxels. And the basic assumption for GeoTOP is that if you know the stratigraphy and you know the lithology, that is something that GeoTOP produces, the stratigraphical unit the voxel belongs to, and the lithological class, then you can determine the parameter of the combination of stratigraphy and lithology from measurements. So we have a sample from sand from a particular stratigraphical unit. You measure the hydraulic conductivity, and then for all the sand of that same stratigraphical unit, you know what the hydraulic conductivity is. Of course, not based on one measurement, but on many measurements. But the idea is that the variation of hydraulic conductivity is determined by the combination of stratigraphy and lithology, and sometimes with depth, depending on the parameter. So using our laboratory, when we can measure hydraulic conductivity from samples, we can add hydraulic conductivity values to the voxels, and that parameterized voxel model can then serve as input for groundwater flow models. Basically, the same applies for all applications in which we make use of GeoTOP. It can be sand and gravel extraction, or something in the built environment, or flooding and drought problems, or land subsidence predictions, or even the site response to induced seismicity. We always need to add a parameter to GeoTOP before we can use it in these applications. For instance, in the built environment, we need to have some understanding of the bearing capacity of sand of a particular stratigraphical unit. We've already discussed hydraulic connectivity, but if we look at land subsidence due to the oxidation of peat, which is a major problem in the west of the Netherlands, then we need something about the oxidation rate of peat. So all the voxels that have peat as a lithological class of a particular stratigraphical unit, we can then populate with the oxidation rate and then start the calculation of land subsidence predictions. The same thing for site response to induced seismicity. If we know what the shear wave velocity or seismic waves is in the voxels, so in the stratigraphical units and lithological classes underneath an area where induced seismicity occurs, then we can also predict the site response and predict areas that are more vulnerable to damage due to induced seismicity and distinguish that from areas that are less vulnerable for that. So using GeoTOP and parameters, we can go a step further to our users, because our users can look at our portals in 3D or in 2D and get a beautiful understanding of geology. But basically, usually, users are not looking for geology, they are looking for a problem they want to solve. And they want to know what is the risk for damage to my house if an induced earthquake occurs here. Or maybe a groundwater modeler wants to know what is the hydraulic resistance of the Holocene deposits. Or a nice example on the left is a map of soft soils plotted over the administrative boundaries of municipalities. This map is being used by the national government to decide how much money each municipality receives for the maintenance of the sewage systems. So if the municipality has to maintain its own sewage system, but if this sewage system, if these pipes are in a peaty area, they need much more maintenance than if they are in a sandy area. So municipalities that are in the west of the country with a lot of peat receive more money for maintenance than other municipalities. And that is determined by this map, which is based on GeoTOP. So that's a very practical application of the GeoTOP model, of a geological model, for something that, well, maybe the people working in the municipality have no idea of the existence even of GeoTOP, but they know about this map and what it means for the amount of money they receive. Well, that's talking a little bit about municipalities, national government. Another thing of the national government is the key registry of the subsurface, which is now in place for 5-6 years or so. It is a law. And this law says that there has to be a key registry of the subsurface, which is basically a database of all subsurface data and of some of the subsurface models, including DGM, REGIS, and GeoTOP. And government agencies like municipalities, but also provinces and water authorities, are obliged to deliver data to the key registry. They're also obliged to use data and the models, and they are obliged to give feedback. So if they find other ground conditions in the subsurface than is predicted by already existing data, or that is being predicted by the models, they have to give feedback and tell us, well, we think that the subsurface at this location is different from what your model, what you think and what you have modeled in GeoTOP or in REGIS. This has some consequences for us. One of them is that usage has increased. The number of times GeoTOP is being used, the number of users as well of GeoTOP has increased a lot. A lot of municipalities are now using GeoTOP, and before this law was in place, they were not looking at GeoTOP. GeoTOP was something for provinces and water authorities, and now all municipalities are also working with it. But it also leads to higher expectations. People expect the models to be of high quality, and they also expect a high update frequency. They will say, I'm obliged to deliver data, and you want me to give feedback, then I also want to see that within a short period of time, that new data is being used to improve your model, or the error that I reported is being corrected for. And we're working on this in a way of thinking, how can we change our way of working from these projects that take 3 years of time to another way of working in which we frequently update the model. And the model is being used, feedback comes from the use, new data is being inputted in the system. In the meantime, our geologists develop new geological insights because they do research and development. This leads into a renewal of the mapping and interpretation, remodeling of the model. Of course, we need to quality control again, and then it feeds back into the key registry. And this cycle must go faster, or we hope that it will work faster than these separate projects that take a very long time. So, almost at the end of this lecture, with some concluding remarks. I think we have quite a strong, well-built workflow to build models of the shallow subsurface of the Netherlands. It is a way in which we choose to have the data, to have a leading role of the data, so the boreholes determine the main outcome of the modeling. But we put a lot of geological knowledge and interpretations into the modeling as well. So it's a combination of data-driven and geological steering. The models have a high level of detail, 150 layers in REGIS, 80 in GeoTOP, and in GeoTOP alone in the Holocene units, we already have 35 different stratigraphical units. We use over 600,000 borehole descriptions in the construction of the model. Computation times are relatively short, but we've come a long way. It used to be very long to process 600,000 boreholes and to model so many layers in REGIS, for instance. So it's partly still work in progress, but we are shortening the computation time every year. Our workflow is highly automated, so it's automated where we can, and if we really feel this is a location, this is a point in the workflow where we want to put in our geological knowledge, then it is, of course, a more manual way of working. And we quantify as much as possible the model uncertainties. We also have some challenges, and some of them I've already mentioned. One of them is that the workflow is quite complicated, and also the software we are using, ECTs and ArcGIS Pro, it's not the most easy software to use. So if we have new employees, there is quite a long learning curve before they can call themselves qualified modelers. We also have long waiting times for geologists to see the effect of their interpretations. And that's why we are working on this experiment of fast-forward modeling. And we've seen that it is quite difficult to incorporate new data types. We are, for instance, now gathering electromagnetical data along the North Sea coast. And we still do not have a proper way of incorporating all that data in GeoTOP, for instance. We've also seen that the time to market is very long. The waiting time for people to, when they deliver new data and they see that that data is being used in the model, that can take many, many years. So we want to work on a way to speed that up. And models are expert products, are geological products, not tailored to the user's needs. So we need more of these maps and other products that tell the people what the subsurface means for their problem, for the thing they are looking for, rather than that we tell them what the stratigraphical unit and the lithological classes at that location. So that is basically the overview of the shallow subsurface models that we produce at TNO, and I thank you for your attention.
Thank you very much, Jan, for your comprehensive presentation of the TNO's approach regarding geomodeling. I can see we are more than 120 today, so to me it's certainly a demonstration of the importance of 3D geological modeling, especially for the geological surveys, but also, of course, a demonstration of the need of sharing experiences such as your expertise at TNO since decades. It's time to discussion. So if you have any question for Jan, please raise your hand or type it in the chat, and we can start with the chat. We have a question in the chat from Annika regarding the time that is spent to checking. I presume it's quality control matter. The question is about how long is it for this kind of checking regarding the whole time spent to the modeling itself.
Yeah, well, check. That's a very good question. The checking in the actual quality control, so when the expert geologists which aren't part of the modeling team are critically assessing the quality of the model, that is not an awful lot of time. Maybe 5% of the total effort. But since our workflow is now highly automated, a lot of the modeling is automated. So you press a button, but then we do a lot of checking ourselves within the modeling project. And I think that is maybe half the time. So running the model, looking at it, seeing that things aren't correct, and then correcting for it, then running the model again. So that is basically the iterative way of working, and that is a real big portion of the total modeling time. Yeah.
Yeah, and I think you partly answered the next question in the chat about how you deal with the inconsistencies in borehole data. So I presume this is part of the checking you were talking about while you are doing the model. Is it correct? So when you have two boreholes at the same place, more or less, that are not consistent in terms of interpretation. Yeah.
No, well, if it's in the same voxel cell but not in the same place, then ECTs can deal with it. Then it's different observations, and it will also look at these two observations, but also at other observations in the neighborhood, and then it can deal with that. If it is exactly the same location, then it's really contradictory. Then we decide beforehand which we think is the best description. And that means that if it's part of the set of these manually interpreted boreholes, then that one is the best. And if there are other boreholes at the same location, then we will look at things like which borehole has the most different intervals in the borehole description. So which borehole is the most detailed. Yeah. We choose that one and ignore the others.
Okay. Sounds clear. Two questions from Sasha about the faults. Are the modeled faults vertical or can be with the other geometry?
Yeah, in the shallow subsurface models, we model the faults as vertical planes. That is an assumption, of course, but in the domain of DGM, REGIS and GeoTOP, it is a fair assumption. So most of the faults in that part of the subsurface are indeed vertical or almost vertical.
And the second question from Sasha about the team. In fact, how many people working in the process for the modeling?
Yeah, we have about 6 people working in the GeoTOP modeling right now, and they work on both on this integrated layer-based model and the voxel model.
Okay, how many? Sorry.
About 6.
Okay.
And the 6 people are working more or less continuously, and of course we'll sometimes need experts, and they work for a short period of time in the project. But these 6 people are really focused on the integrated layer-based model and the voxel model.
Okay, the full-time job for them, I presume.
Yeah.
Next question from Charles. You displayed a slide quite impressive with the balls available, and he asked about the density for GeoTOP, density of balls.
Yes, well, we have about 40,000 square kilometers and about 600,000 boreholes. So that's so you can do the math.
Maybe
so it is not often the case that referring to the previous question, doesn't occur that many times that there are more than one borehole in one voxel.
Yeah, it's a remark from me, but maybe it's also a reason why you can automate the process, because you have a lot of data also and a good density. So it's easier in a way to have an automation of the process.
Yeah.
Okay, a question from Nico. Is there a detailed report about the use and or method workflow of the DGM-deep model, especially regarding seismic interpretation or log correlation?
Yeah, there's a scientific paper on the DGM-deep model. And there is also, but that is still in press, there's going to be a new book about Dutch geology, in which there is a chapter about the 3 models that I've discussed today, and also about the DGM-deep model. So that will be published this summer. So
okay,
if you
so
send me an email if you're interested, and I can put you on a list and give you a copy of the chapter later this year.
Thank you. Another question from Isabel. Can you detail which kind of data are collected in the BRO registry, or the geotechnical data, for instance?
Yes, so geotechnical data, the CPTs, the cone penetration tests, which are there are millions of CPTs in the Netherlands. Of only at this point in time, only a small portion is in the key registry. But now, if a municipality wants to create a new residential area and they make a lot of CPTs, and they are obliged to deliver it to the key registry. So the number of CPTs in the database is growing almost on a daily basis. So that's an enormous amount of data that we are receiving in the registry. And we're also just looking at how can we benefit from geotechnical data in the construction of GeoTOP, for instance. Another data is, of course, borehole descriptions, and also groundwater levels, which are being measured in time, things like that.
So another question from Emilio related to the amount of data as well, and about computing. Is there any requirement of high performance computing for completing this kind of models?
Yes, we've experimented with high performance computing cluster, but we found out that ECTS is not really well suited for that kind of environment. Because of licensing issues, basically, not because of the software itself. So what we generally do is that we have a set of dedicated PCs, high-end PCs, which each run different chunks of the GeoTOP model at the same time. And that does the job. So it's quite simple infrastructure that we use to do the calculations. And the layer-based model is running on a single computer overnight. So that's not the computation time of the layer-based model is already very short.
Okay, another question about BRO from Michael, and about standards. How do you manage to have a harmonized description of borehole data? Do you use a specific standard, international or also?
Yeah, so all the BRO data is being standardized, and the standardization is the outcome of many discussions between TNO, who was designing the BRO, and the users and the deliverers of the data. So that's always the way in which we work in the Netherlands. That we never say you have to do it this way. We always discuss it with all the stakeholders, and then the outcome of that discussion defines the standard in this case. And then that standard is being followed by all users. So if you deliver a CPT or a borehole description to the BRO, you have to do it in a standardized way. But somehow in the previous years when we were developing the system, you were involved as a user, or representatives of your community were involved in developing that standard. And you will recognize bits and pieces of international standards in it. So usually we use an international standard as starting point, but at many places it is adjusted to the typical Dutch circumstances of the subsurface. Yep.
Yeah, the next one is from Katerina about the quality criteria you used for calculating the uncertainties. What are these criteria, these uncertainty criteria? Can you tell me about that?
It's a very good question, because right now we only estimate the model uncertainty. So how good is the model able to estimate, to predict what is in the subsurface based on the boreholes that we put in as data points? It doesn't model, it doesn't show the uncertainty related to the data itself. So given the data as fact, what then is the uncertainty? But of course the data itself isn't a fact, it also has an associated uncertainty. And we're still experimenting, and we're doing that already for a long time, to think about what are ways to estimate the uncertainty of our borehole data, which is a very hard thing to do, especially for those borehole descriptions that are maybe 30 or 40 years old.
Yeah. A question from Herald: how important are seismic data in comparison with the other data? So a matter of weight of data.
Yeah, well, for the DGM-deep model, they are extremely important, because basically the whole model is based on seismic data, and the seismic interpretation is then tied to the wells, but seismic data is leading. And for the shallow subsurface model, the lowermost units are also using seismic data, but then still the shallow boreholes that reach the depth, the lowermost parts of the model, are in the lead. So the shallow model seismic data is an aid, and in the DGM-deep model it's paramount, and the deep model cannot be made without seismic data.
Yeah. So still regarding the geophysical data, a question from Annika, because you said somewhere that it was difficult to integrate geophysical data or new kind of data. Is it a matter of the fact that these data are two-dimensional, or because you work mostly with boreholes, but it's not the case, as you said, for deep models. But what is the issue with the geophysical data you cannot integrate, or not yet?
Yeah, but basically you're already answering the question here. So that's what we need to do if we want, for instance, in a layer-based model, you want to use a lot of measurements from continuous data, then we have to convert it into point data. And just tell ECTs that these are bases observed in drill holes, and then it will run. But it is not always the most satisfying way to deal with this beautiful continuous data. So we're not really satisfied about the method that we have right now, in which we convert everything to point data as if it were drill holes. No.
Okay, the next one is not really for you, Jan, but the question is, will be the lecture available anywhere? So it will be available, it is recorded, and it will be available on the EGS media. So Irena will work on that to make it available, and you will be informed, of course, when it will be available. We have a question from Charles about the communication of geological uncertainties to the general public. It was one, I think, of your challenges you mentioned on the last slide, to ensure that they are aware of the limitation of the model, of course.
Yes. Yeah, we'll deliver the uncertainties with the model. And in case of GeoTOP, if you create a cross-section on the portal, you can also look at the probabilities. But it's very difficult to do this. It's very difficult, especially the general public. It's very difficult to explain that you do not know something for sure, but that you make an estimate. But also for specialists. Specialists tend to ask for uncertainties, and then you give it to them, and then they ask us, what should I do with it? It's sometimes a bit frustrating.
Yeah, knowing or quantifying uncertainty is very important.
We put a lot of effort in quantifying uncertainty, and we know that we're not there yet. We can quantify model uncertainty, like we discussed a couple of minutes ago, and we also need to incorporate data uncertainty.
Yeah, that's right.
But if we deliver it, who is using it? I don't know.
Yeah, but once you have quantified uncertainty, when it's possible, the next step is to share with people, and it's certainly not the same way of sharing with the scientists or with of course general public or stakeholders and so on. Yeah. So it's also an important issue regarding uncertainty, the way they are shared. Yeah. Another question from Peter: what is the accuracy of the measurement in the boreholes?
Yes.
So this is what you said about the certainties in the boreholes themselves.
Yeah, it depends on the borehole. So we have boreholes that are cored continuously. And basically, the sediment is taken out of the ground as a continuous core. You can lay it out on the table and then describe it in very high detail. Those are the best, of course. That's also the kind of boreholes we use to collect samples to measure, for instance, hydraulic conductivity. But there are also boreholes that are being drilled and sediment is being flushed to the surface with water, and then you end up with buckets with sediment mixed together, and you roughly know that the bucket of sediment was from 40 to 42 meters in the depth. Well, that is quite inaccurate, of course. And everything is in the same database. Of course, we know from the borehole description what method was being used, and that helps. But we tend to use the inaccurate boreholes as well as the very accurate ones. Because if we only select the ones that have high detail, we no longer have 600,000 boreholes. Then we have a lot less.
Yeah. Okay. So feel free to raise your hand if you have other question. We are not that numerous now. We're still 90. But anyway, you can type it in the chat, of course. But you can also ask directly Jan with your microphone. I have a question for you, Jan. You told us about the fact that building subsurface geological models is in the Dutch law. I wonder if you have more information information about of such a law was made possible?
How we did it in the Netherlands, or do you mean if it's
No,
something...
how it was constructed as a law? I mean, it's not by chance. There was certainly some work, some jobs, some lobbying. I don't know that
Yeah,
has
there
been
was a
made.
lot of lobbying involved from the...
I don't know if you have any information or any historical on that. Yeah.
Yeah, and the more technical parts of the law, because it's quite a big document, were also written by with the help of the Geological Survey. So of course it's civil servants who really know how to write a law properly.
Yeah.
That's do the final writing. But well, actually the law mentions models.
I mean at the beginning, but maybe you don't have the information. I don't know. At the beginning, was it a kind of lobby from the Geological Survey towards politicians, or yeah? Mm-hmm.
Yeah, that's correct.
Yeah, no, I presume it's important to know because
but the whole idea for the national government is that there's a set of key registries ranging from things like addresses and personal information of all the citizens and cadastral accounts, so houses, company buildings, offices, and also the subsurface. Also topography is a key registry, and it is basically the single point where you, as a government, know here is the authentic information about a certain topic. So if I need the address of a citizen, then I go to that key registry, and I need not to go to any other database. The correct address, the authentic address of that citizen is in the key registry. And the same applies now for the subsurface. If we want to know what the subsurface looks like, what data is already available, and what the models estimate, then you only need to go to the key registry. You do not have to think of other databases or data sets. That is the single point of place, the single place where you have to look for the data on the subsurface. And that makes it for people using the key registry, so municipalities and water authorities and provinces, a lot easier to work. So they don't have to look everywhere for data. They only have to look at it one single place. That is the gain of the government by this key registry.
Thank you. A couple of questions in the chat from Robert regarding boreholes data. Do you have lithostratigraphic information on all of the borehole you mentioned? And if not, how do you use the information in the model? I presume if you have not this information, is the borehole useful anyway for the model? Or do you have the information on all of the boreholes regarding lithostratigraphy?
Yeah, well, the boreholes are delivered in the database with only a description. So it will tell you the sand or clay or peat and what the admixtures are and what the shell content is and things like that. And then in the modeling process, we add a little stratigraphic information to it. And for this large amount of boreholes, and especially the shallow ones, which are handmade, we do this using these automated procedures. So maps and criteria are combined in Python scripts, and the Python scripts looks through the description of the borehole and then decides this between this top and between this base is a particular stratigraphical unit. And there's these other data sets. There's 26,500 boreholes, so much less than 600,000, which have been over the years interpreted by hand by trained geologists.
Okay, and a question from Annika. I think, if I understand well, it is related to the modeling of very thin formations compared to the X and Y dimensions, especially, for instance, for glaciofluvial sediments formations. How it works with this kind of rather narrow and long depositional elements in the modeling.
Now, if they are really much smaller than 100 meters, then they are just below resolution, then we cannot model them. But sometimes, for instance, in Holocene fluvial channel belts, so the difference from glacial fluvial sediments, of course, but also long and small, we tend to make them a little bit broader to make sure that cells connect to each other, that you do not get a fragmented channel, but a continuous channel. It will be a little bit overestimated in the width because of we model it a bit bigger than it actually is, but then we know for sure that we have a continuous volume, in which, for instance, in a groundwater flow model, water can flow through. But we do not have a solution for things that are really much smaller than 100 meters. And we need to make a more detailed model that we sometimes do, not in the national models, but in local models for particular purpose. When somebody asks us, well, I have these glacial fluvial elements in my subsurface, and I want to have a good idea where they are and how they are configured, then we can make a more detailed model. We can make voxels that are much smaller than 100 meters.
That's certainly a tricky issue, especially when you deal with voxels, of course. We have yes, another question. How do you handle modeling glassy tectonically distributed sediments?
Yeah, we have ice pushed ridges in the Netherlands. There's this part of GeoTOP close to TNO in Utrecht has some of these ridges, and they are sediments, fluvial sediments for the River Rhine, which are pushed by ice, and so the strata dip towards the position of the glacier. And what we do in the way is the same way as the dipping surfaces in the southern part of the Netherlands, of which I showed an example. We look at the general trend of the dipping of the strata after they were disturbed by glacial tectonics, like the present day position. We flatten them to the original deposition in the fluvial setting, before they were disturbed. We do the interpolation, and then we set the whole system back to the disturbed position of today. So then you can see some effects of the glacial tectonic disturbance in the voxel model. And for instance, what you then can see that you have dipping clay layers within these more or less sandy hills, and these clay layers have a very interesting role in the water, in the way groundwater flows through these glacial tectonic or ice-pushed ridges.
Okay, so
it's difficult because there are not a lot of boreholes on these ridges, and so we do what we can, and it gives a nice first impression, but it is difficult to do. Yeah.
And we have maybe one of the last question for today from Nicola. It's more comment than a question regarding what you said about moving from Isatis maybe to an open source solution like GenPy, because the 3D modeling approach is really different.
Yeah.
Nicolas says that it would be interesting to see the difference between the two ways of modeling with your data, but maybe the density of the boreholes would make that the difference not be so much significant or not. Have you made some tests already, or?
Yeah, we've done some first tests in an area in the south of the country where we also have some faults. And Nicolai is completely right that in general, the high data density makes sure that the surfaces are very similar to what we model in ECTs. The GEMPI is much faster than ECTs and than the whole procedure that we've made in ECTs, but it has quite some difficulty to handle the faults. So we still have to look into that.
Yep.
But I agree, it's really interesting to see. It's also one of the reasons that we are trying GEMPI, just to test a very different approach to estimating the geometry of the subsurface than what we have been doing for the last, I don't know, 20 years or so. Yeah.
Okay, thank you. So I see no more question in the chat. If you want to ask a very last question, again, raise your hand or write it. Otherwise, I think it's time to conclude now. So thank you again, Jan, for your presentation today.
You're most welcome.
Thank you to you all for your participation, questions, and watching. And
Yeah.
see you for at the next webinar. Bye bye.
Yeah. Thank you all, and thank you for the very good questions, by the way.